Ladies and gentlemen, I want you to meet two of my good friends right here. This person on the left, his name is Mac, aka Return of the Mac. And his buddy on the right hand side, this is PC Bill right here. His name is PC Bill, Bill PC. And these two are having an argument. They're sitting there in their bubbles because they're built off protocols. They really can't see the network, but they're still yelling at each other because they know something is going on. So what happened was, Return of the Mac says, where do I send this packet? Because, 90s hip hop is the best ever in the world. So he wants to send a packet to PC Bill. Bill says, I don't know. You're supposed to route it. Because Bill's all about the early 2000s hip hop. Return of the Mac says, hey, I need to send this packet, man. Where are we at? PC Bill says, I don't know. You're supposed to route it. Return of the Mac says, yo, I need to send it, man. Where we going here? PC Bill says, nope, you're supposed to route it. And they just keep going back and forward. Ladies and gentlemen, welcome to Module 8, the network layer. Without the network layer, okay, that deals with the IP addresses. Let's go back to these pictures here. This company cannot operate, right? If we don't have the actual addresses, that data cannot move where it needs to get to. Those packages that you physically send in the mail cannot get to its final destination without having the proper IP addresses, right? So very, very important. Very important. So let's get into this. Module 8, the network layer. So in this video, we're going to explain how the network uses IP protocols for reliable communications. Explain the role of the major header fields, IP version 4 packet, IP version 6. Explain the role of the major header field in IP version 6. How a host routes. Explain network devices use routing tables to direct packets to a destination network. Okay. And the routing tables. Explain the function of the routing table fields. So let's take a look at the network layer characteristics. So the network layer provides services to allow devices to exchange data. So provide services, right? So previous videos, we went over layer 1, layer 2. That's those data packets that are coming in. Now we're going to decapsulate those packets, and now we're starting to work that data all the way up the OSI layer. But in order to do that, we've got to have an address. We have to have that IP version 4, IP version 6, network layer, layer 3 address. The network layer performs 4 basic options: addressing end devices, encapsulations, routing, and de-encapsulations. Yeah, that's exactly what I was just referring to, being able to take that information and encapsulate it and then decapsulate it. That's opening that package, saying, oh, this belongs to such and such, put it back in the package, and it gets to where it needs to get to. IP encapsulates the transport layer segment. IP can use either IP version 4 or IP version 6. Okay. Packet and is not impacted for the layer 4 segment. So we're just dealing with just layer 3. IP packet will be examined by all layer 3 devices as it traverses through the network. The IP address does not exchange from source to destination. NAT will change address, but will be discussed in a later module. Yes, NAT. This stands for send me an email if you know what that actually stands for. And also, if you know what that stands for, what NAT stands for, I want to know why NAT exists, and I want to know what version IP addresses does NAT refer to. Like, what does it help solve? Specifically, which IP version when it comes to NAT. IP is meant to have low overhead and may be described as connectionless. That's that UDP. Best effort and media dependent. IP is connectionless. IP does not establish a connection with the destination before sending a packet. There's no control information needed, synchronization, acknowledgement. So it just sends it. It's kind of like, when you're taking a ball and you're hoping to hit something, hopefully not a window or anything like that, but you're throwing it and you kind of look away and you hope that it doesn't hit anything, but maybe it does hit something, right? So it doesn't establish that connection before it actually sends it, right? It's like, I'm just gonna shoot and just forget about it. Hopefully that gets there. Kind of like playing basketball, shooting up those prayers. Oh, I hope it gets there, right? The destination will receive the packet when it arrives, but no pre-notifications are sent by the IP. If there is a need for connection-oriented traffic, then another protocol will handle this, which is TCP, okay, which is the Transmission Control Protocol. So going back to this, let me make sure you guys understand this. The destination will receive the packet when it arrives, but no pre-notifications that are sent by the IP address. I want you to think of when you go into the UPS store or when you go into FedEx or whatever, okay? And you go to send that mail. You want to send that mail out, but you don't care how it gets there. You want it to get there as fast as possible, but you're not looking for that receipt. You're not looking for that notification or that text message or that that indication that there was a delivery. You basically pay the fee and you pray that the information gets there like it needs to get there. That's essentially what connectionless is, right? I just want to send it. I don't care. I hope and pray that it gets there. I hope it doesn't get sent back. So that's kind of how that works there. IP is best effort. IP will not guarantee delivery of the packet. IP has reduced overhead since there is no mechanism to resend the data that it is not received. So you can't resend it. It just, like I said, going back to those basketball prayers. Oh, hope it goes in. IP does not expect acknowledgments. It's not looking for a, hey, did you receive it? Yes, I did. Thank you very much. It's not looking for anything like that. IP does not know if the other devices is operational or if it received the actual packet. Okay. So packets are routed through the network quickly. Some packets may be lost during the actual route. So again, it is connectionless. It is the best effort. It's how fast we can get there. We just pray and hope that the information gets there. Yes, this is very important. IP is unreliable. Very similar to when you send that package in the mail during Christmas time and you don't get that delivery confirmation receipt. That's very unreliable. Mr. UPS guy or FedEx or whoever can decide to, not saying people would steal, but something can fall off the truck and we have no idea where that is, right? IP cannot retransmit after an error. IP cannot realign out of sequence. IP must rely on other protocols for this to function. IP is media independent. IP does not concern itself with the type of frame required at the data link layer or the media type at the physical layer. IP can be sent over any media type, copper, fiber, or wireless. Very important. Copper, fiber, or wireless. Does not matter. As long as it's connected, you're good to go. That thing's got IP address. We're ready to roll. The network layer will be established with the maximum transmission unit, MTUs. Network layer receives this from control information sent by the data link layer. The network then establishes the MTU size. So it figures out, once it gets all the information, it figures out how big that MTU size is going to be. Fragmentation is when the layer 3 splits the IP version packet into smaller units. So I believe I did talk about this in my other videos. If you think about that desk, like if you're shipping a big desk during Christmas time, got a big desk, comes in big pieces, typically that desk is not going to be in one big box, right? It's going to be split up. It's going to be fragmented. Kind of the same thing as IPv4. It's going to be delivered into some smaller pieces. Yes, fragmenting causes latency. It's going to be a little slow, right? You're waiting on your packages. Package 1 of 3 gets there. Package 2 of 3, 3 of 3. It may take certain times of the day for those packages to get there. IP version 6 does not fragment packets because it's longer, 128 bits, right? Example, router goes from Ethernet to a slow WAN with a smaller MTU. use here, IP version 4 packet. IP version 4 is primarily communication protocol for the network layer. The network layer header has many purposes. It ensures that the packet is sent in the correct direction to the destination. It contains information for the network layer processing in various fields. We're going to take a look at that here in just a little bit. The information in the header is used by all layer 3 devices that handle packets, routers, right? Those deal with a lot of layer 3. So let's take a look at, this is a sample header field. Okay, we have 4 bytes. The whole deal is within 20 bytes here. So it is in binary. Remember those binaries, the ones and zeros, all that good stuff. Contains several fields of information. Diagram is read from left to right, 4 bytes per line from left to right. So we have the different version, identifications, time to live. Here's the protocol. Here's the source IP, destination IP, right? So this is layer 3 in this area here. 2 of the most important fields are the source and destination. That's correct, right? These 2 areas right here, these are the most important. The reason why is because that data needs to get there, right? It needs to know how to get there and where it needs to go. So let's talk about the different types of fields as it gets into the IP version 4 header. We're going to talk about these items here. Now, before we do that, let me go ahead and open up Wireshark. Let's move this up here. I'm actually going to split screen this because I'm going to open up command prompt here in a minute. So I'm going to collect some, we're going to take a look at some packets, IP version 4 packets, using Wireshark here for a second. Okay, so hope you can see my screen here. I'm in a full screen here so I get myself out of the way. Okay. So I've got IP version 4 going. I'm sorry, I've got Wireshark going. I apologize. Got Wireshark going, and I've got a lot of data moving for the network, right? This is all typically, this is the OSI layer moving as it needs to be. Now, what I'm going to do while that's going, I am going to run a ping command. You see, I've already done it before. I'm going to do it again. I'm going to run the ping command to Google 8.8.8.8. Okay, I'm sending a Marco Polo to Google. So I'm going to give it some time so we can kind of capture the data. I think that's good now. So I think the data is captured. So let's take a look at my screen here. All right. I'm going to go up here in the header, and I'm going to type in ICMP, which is wonderful pings. Okay, and let's see if we can find those packets. Oh, I think we do have something here. So let's do some inspections here. So obviously this is my internal IP address. And I sent a Marco Polo to 8.8.8.8, which essentially is Google. So let's click on this first packet. So as we're looking at some of the other videos, here's the frame. Goes out of the layer 1. Then it hits layer 2, it's destination. If you remember ARP, okay, MAC addresses, right? Destination MAC addresses. Now let's take a look at IP version 4. Let's collapse these down a little bit so you can see. Now here's a network layer. And as you can see here, it has a source address, which is right here. It's kind of hard to see it. And then a destination, which is 8.8.8.8. So essentially it captured this data, right? The Wireshark was able to capture that ping command. And if we look at the ICMP protocol, let's look at this here. It's saying that everything checks out. Everything's good. Echoes got there, right? All the echo pings got to where it needs to get there. And the response was good. So this is a good example of running Wireshark and just doing a simple ping to different websites, right? So in this case, all I did was just ping Google, so you can actually see that IP version 4 header as it goes through. IP version 6 packets. IP version 4 has three major limitations, right? IP version 4 depletion, we have basically run out of IP version 4 addresses. That's a little hint to the question that I asked you earlier. Little hint. Lack of end-to-end connectivity to make IP version 4 survive this long, private addressing, and NAT. There's another little clue. I still want you to email me. Let me know what you think about that. Increased network complexity, NAT, there's NAT again, was meant as a temporary solution. It creates issues in the network such as side effects, manipulating network headers, addressing latency issues, and all that stuff. So still need you to send me an email on what all that is and why that exists, because I want you to do a little bit of research on that. Okay? Now, let's take a look at IP version 6, because obviously there's a lot of information going on here. IP version 4 has 32 bits. IP version 6 has 128 bits. Okay, that is a lot of bits. I don't think you'll have any issues with all of that there. All right. So with IP version 6, there's a lot more addresses available. There's a lot more opportunities for devices to connect. And as you see here, improve packet handling, simplify header, fewer fields. Here goes another hint on what I was asking earlier. It eliminates the need for NAT. Again, not going to tell you what that is, right? But again, it solves a lot of issues with having IP version 6. IP version 4 packet header fields in the IP version 6 packet header. So IP version 6 header is simplified but not smaller. So as you can see, this definitely a lot bigger, but at the same time, it's not smaller, right? IP version 4 fields were removed to improve performance. Some IP version fields are removed to improve performance: flag, fragment, offset, and the header checksum. Went too far. IP version 6 is simplified but not smaller. The header is fixed in 40 bits or octets. Several IP version 4 fields were removed to improve the performance, right? So we wanted to get that out of there. Makes things a lot quicker having IP version 6. Some IP version 4 fields were removed to improve performance: flag, fragment, offset, and the header checksum. So an IP version 6 packer header. Okay, we can look at the version. This will be V6 as opposed to V4. Okay, 4 bits in a 4-bit field. The traffic class used for quality of service, equivalent to DS field. The flow table, we have the payload length, 16 bits. We have the next header, which is the ICMP, TCP, or UDP, Transmission Control Protocol, a unit datagram protocol. One is connectionless, one does require the connection. And then we have the hop limit, replaces the time to live field, layer 3. And then we have the source. I did it again, sorry. We have the source IP version 4 address, which is 128-bit source address, and the destination IP4 address, which is essentially the 128-bit destination address. So those are essentially the equivalents there. IP version 6 packet may also contain extension headers. Extension headers characteristics provide optional network layer information and are placed between IP version 6 headers and the payload. May be used for fragmentation, security, mobility, and support. Unlike IP version 4, routers do not fragment IP version 6, so it can handle it. That's one of the things. It can handle that information because it doesn't need to be fragmented. How a host routes. Host forwarding decisions. Packets are always created at the source. Each host device creates their own routing table. A host can send packets to the following itself, which is that loopback, that 127.0.0.0.1, IP version 4, and then IP version 6. Local host destinations is on the same local area network. Remote host devices are not on the same local area network, right? Because they're in a different location. Host forwarding decision continue. The source device determines whether the destination is local or remote, right? It checks its routing table to say, where does this need to go to? Is this on my network? If it's not, I'm going to send it out of my gateway, right? IP version 4 uses its own IP address and subnet mask along with the destination IP address. IP version 6 uses the network address and prefix advertised by the local router. So very important. These two are very different. So IP version 4 is going to use a subnet mask and IP addresses, right? So it needs to know these. In order for IP version 4 to work correctly, they need to be on the same subnet. That's that same zip code. And they need to have the same IP addresses all within the same zip code. IP version 6, the router, the local router gives all that information out. Local traffic is dumped onto the host interface to be handled by intermediary device. Remote traffic is forwarded directly to the default gateway on the local area network. Okay, so the default gateway. A router or a layer 3 switch can be a default gateway. Layer 3 means that it deals with network IP addresses. Features of the DGW, it must have an IP address in the same range as the rest of the local area networks. It can accept data from the local network and is capable of forwarding traffic off the local area network. So if it doesn't see it, it sends it out where it needs to go. And it can route to other networks. Very important for those broadcast domains to be able to talk to each other. They've got to have a router in between to route the information. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the local area network. So it's got to have the right gateway. So if you're ever working in Packet Tracer and you're configuring your devices and you have everything hooked up to a switch and it goes to the router, very important that when you're doing your IP version 4 addressing, when you go to configure those end devices, that gateway needs to match the same gateway IP address of the router, because that's the gateway. So in order for those machines to talk to each other, the gateway address needs to be the same as the router. Very, very important. A host routes to the default gateway. The host will know the default gateway, either statically or through DHCP, which Data Host Connection Protocol. I want you to send me an email what port that uses. DHCP. I want to know what port that uses. IP version 6 sends a default gateway through a router solicitation or can be configured manually. So default gateway is static route, which will be the last resort route in the routing table. All devices on local network will need the default gateway of the router if they intend to send traffic remotely. Very important. Host routing tables. In this example, they typed in the netstat-r command or route print. And this is essentially a routing table on the Windows machine. I know it looks a little gibberish. Let's see if we can kind of go through this here just a little bit. But as you can see here, the network, these are all the network destinations. These are the subnet masks. Remember, everything's got to be on the same subnet. And the default gateway. So essentially this first line, if the data that it needs to send out, like if there's an end device on a network, and if it's not on the same network, it's going to send it out the gateway, right? So if you're sitting in your house and you want to deliver something to your buddy in New York, well, nobody in your house is in New York because you're in California. You're going to send it out of the post office. It's going to go out the gateway. And that interface essentially is going to be your home address, right? That's where that's going to go. Now, if it's somebody in your house that you want to deliver the information, that's where you get the on link. This does not need a router. Does not need a router at all. So in this example, destination, which is 127.0.0.0, this is essentially the loopback, kind of test your own connections. Notice that there's an on link. There's no gateway because it's all internal network. And same thing here. 192.168.10.0. Now this would be the network ID of this network, because I can tell this is a WAC 24 network, 255.255.255.0. Here's a net ID, and this would be the broadcast ID right here as well. So essentially all that traffic too, everything's internal, so it does not need a gateway. Introduction to routing. What happens when the router receives a frame from the host device? The packet arrives on the gigabit 000 interface of the router and de-encapsulates the layer 2 frame header and trailer. Router 1 examines the destination IP version 4 address. So it says, hey, what is this? It opens it up. What is this stuff? I need to see what this is. And the packet searches for the best match IP version 4 routing table. So that routing table, it's going to go to that routing table. So it's going to take a look to see, this is where that needs to go. We're going to look at that routing table. The route entry indicates that this packet is to be forwarded to router number 2. Router 1 encapsulates the packet into a new Ethernet header and trailer and forwards the packet to the next hop router. So if it's not within that particular network, it's going to send it out the gateway. It's going to hit the next area so it can actually get to where it needs to get to. Let me kind of go back to this graphic here for a quick second. I want you to think of this routing table. I want you to think of a big UPS facility or a big Amazon facility located in some big city. If a request were to come in and the shipping manager says, we need to get this information out, they're going to look at some type of a table that's going to have all of the routes on where that data needs to go, right? Where that city or what street that needs to go to, what zip code that needs to go to. This is very similar to that. Computer is going to do the same thing as far as the protocols. It's going to look at the table. It's going to refer to the table as to where it needs to go. Very similar to that shipping manager. It's going to look at the list and say, I see where it needs to go. It's supposed to go on this truck, and we're going to send it out on this truck here. Okay, so we looked at this one already. Let's move on here. IP routing tables. IP router routing table, excuse me. There are 3 types of routes in a routing table. We have directly connected. These routes are automatically added by the router, provided the interface is active and has addressing. So these are the connections that are already there. Remote, these are the routes that the router does not have direct connections to and may be learned manually with a static route. Dynamically, by using a routing protocol to have the routers share the information with each other. Now the default route, this forwards all traffic to a specific direction when there is not a match in the routing table. So if it's nothing in the network, if it doesn't know where it needs to go, it automatically sends it out the default gateway. It's gonna send it out. It's gonna be the default route. And these are some static route characteristics. Must be configured manually. Must be adjusted manually by the administrator where there is a change in the topology. So if something were to change in this information, if items were to change, things of that nature, it would need to be reconfigured. Good for small redundant networks. I agree with that. Often used in conjunction with a dynamic routing protocol for configuring a default route. And here's another example. Dynamic routing. Discover remote networks, maintain up-to-date information, chooses the best path for the destination and wants to know the quickest way to get there. Find the new best path where there is a topology change. So if there's something that's changed in the network, it's that routing table is going to learn again. And dynamic routing can also share static routes with other routers. Introduction to an IP version 4 routing table. The show IP route command shows the following sources. So if you were to go into a router, type in show IP route, this is the information you're going to get. And there's a plethora of information. Notice the different WAC numbers here. Obviously, these are different subnet masks. Very important. The reason why these are different subnet masks is these are probably different subnets, different broadcast domains. So when you're doing your packet tracers, when you have 2 different subnets or 2 different broadcast domains that are trying to talk to each other, both of those ends on those routers, they got to be configured correctly. Each one of those have to be configured correctly there. This command shows types of routes, directly connected, C and L, remote routes, OD, and then default routes with the letter S. So when you do packet tracer, type in show IP route, you will get that information there. All right, ladies and gentlemen, that is going to conclude Module 8. Make sure you're practicing your packet tracers, and you have a great day. See you on the next video.